Hello, welcome to Advanced Composites. Today is the 4th day of the ongoing week, which is the 6th week of this course, and what we will do is we will develop a solution for the second situation for a semi-infinite plate, that is for case B. Once again, in this case, the lamination sequence is still symmetric. So, these equations which we have developed, they are still valid for u, v, w, nx, ny, nxy, mx, my and mxy. They are still valid, but what will happen is that maybe the values of u1, u2, these integration constants, they may change, they may or may not change, but it all depends on the nature of boundary conditions. So, what we will do is we will once again implement the boundary conditions and look at the solution of the system and see what it tells us. So, these are the this is the starting point, and let us look at the solution. So, once again we are going to do this for case B, and the boundary conditions are such that u minus, v minus, w minus, mx minus and u plus, v plus, w plus and mx plus, they are all 0. And the lamination sequence, again we said that it is not changing, it is still 0, 90 symmetric. So, the equations shown in this slide, they are still valid. So, now let us look at, so we will start now implementing the boundary conditions. So, we will start right away from u. So, u naught is equal to C1x plus C5 into 1 over A11, and we know that u is equal to 0 at x is equal to plus minus a by 2. Okay. So, it's a small error of notation, this should be u subscript. So, this is equal to 0. So, if I implement these boundary conditions, I get that C1 is equal to C5 is equal to 0. If I apply x is equal to a by 2, u is 0, I get one equation, and then another equation is C5 minus C1 a over 2 is 0. So, from this I get this thing as 0. The second equation is Vx is equal to C2x plus C6 divided by A66. So, V naught is equal to C2x plus C6 into 1 over A66, and then we know that V naught is equal to 0 at x is equal to plus minus a by 2. So, from this we get C2 is equal to C6 is equal to 0. We get this once again. The third condition is, so what have we done till so far? We have implemented 4 boundary conditions. We have implemented this BC, all the 4 BCs in u and v. Now, we are still left with the boundary conditions related to w and mx. So, let us look at the other condition. So, first we will try to implement the condition for mx. Okay. So, mx is equal to minus qx square over 2 plus c3x plus c4. So, we will implement it. Mx is equal to minus qx square over 2 plus c3x plus c4, and we know that mx equals 0 at x is equal to plus minus a over 2. So, we get 2 equations, 0 equals minus q a square over 8 plus C3 a over 2 plus C4, and the other one is 0 equals minus QA square over 8 minus C3 times a over 2 plus C4. So, from these we once again get C3 equals 0 and C4 equals QA square over 8. So, I end up with Mx as QA square over 2 1 minus x over a whole square. So, now we have implemented 6 boundary conditions. So, we have also implemented the BCs on Mx, and the 2 boundary conditions which are left are related to W, out of plane displacement. The relation for W is this long thing, and if I write this, what I find is, so let us write it down, W naught. So, this is equal to minus 1 over D11 minus QX4 over 24 plus C3 x cube over 6 plus C4 x square over 2 plus C7 x plus C8. Okay. And we have also already said that C3 is 0 here, from here. So, this term, it goes to 0, and now we implement the boundary conditions that W naught equals 0 at x is equal to plus minus a by 2. Okay. And we also know that C4 is QA square over 8. So, this thing is QA square over 8. Okay. So, now we have 2 conditions and 2 unknowns, C7 and C8, and we can calculate that, and if we do all the math correct, this is what we get. So, I will just write down the final result. So, W naught x equals QA4 over 384 16 x over a 4 minus 24 x over a square plus 5. Okay. So, this is the solution we get from this. So, we will come. Yes. So, there should be no, there is no D11, this is what it is. So, let us compile all the results in this case, and if you compile all the results, you will find that the solution is identical as this one. So, this was the solution for case A, and this is also the solution when we solve and implement all the boundary conditions for case B. So, what we find in this case is that the solution for case A and case B is identical. Okay. And now you will be wondering that why is it the case, because the boundary conditions in both the cases are different. The boundary conditions, if you remember, in case A are different than those in case B, specifically at x is equal to plus a over 2 end. Okay. So, you may be wondering that what is the problem, what is the reason why, despite the fact that these two plates have different boundary conditions, the solution comes out as same. That is the question. So, what we will do is that we will spend next few minutes trying to explain why is it that the solution is different. Okay. Let us go back to our original differential equations. So, what are the governing differential equations? Del nx over del x plus del nxy over del y equals 0, del nxy over del x plus del ny over del y equals 0, and del 2 mx over del x square plus twice of del 2 mxy over del x del y plus second derivative of my with respect to y plus qxy is equal to 0. These are the three differential equations, and the way we had developed these three differential equations was that this first equation was related to the force equilibrium condition, that this is sum of all the forces in the x direction is 0, right. The second differential equation came out when we equated all the forces in the y direction to be 0, if you remember during the derivation. And this differential equation is essentially a combination of three differential equations which we have combined together. What were those three differential equations related to? Sum of all the forces in z direction is equal to 0. The second one was sum of moments about x axis, that equals 0, and the third equation was sum of moments about y axis, their sum was 0. Okay. So, this third differential equation we had shown is a combination of three other differential equations. They were all first order differential equations. We combined them and we came up with the third differential equation. Now, when you look at this, so this is fx is equal to 0, fy is equal to 0. So, if I look at my plate, this is my x axis, this is the y axis, and this is the z axis. Okay. So, when I add up all the forces in the x direction to be 0, then I get this first differential equation. What does it mean? That the first differential equation relates to forces which are in the plane of the plate, because they are acting in the x direction. So, these forces are in plane of the plate. So, this is an in plane equation. Second one is sum of forces in the y direction, that equals 0, and the consequential differential equation is the second one, which is del nxy with respect to x plus del ny with respect to y is 0. So, here all the forces are in the y direction, again they are in the plane of the plate. So, again this is again in plane equilibrium. In plane equation. But all the remaining three equations, which are sum of fz is equal to 0 and moments, see moments can never be, see these moments were about x axis. So, if there is something about x axis, the moment will be out of the plane, and similarly moments about y axis will also be out of the plane, and fz is also out of the plane. So, this third equation is out of plane equation. This is out of plane. Actually, I should not call it. So the first equation and the second equation, they tell us about in plane equilibrium, and the third equation tells us about out of plane equilibrium. Okay. So, these two, they tell us about in plane part of the problem. And the third equation tells us about out of plane problem. So, if you solve, so that tells, So, that is about out of the plane problem, the third equation, and the first two equations are about in plane part of the problem. So, this is one thing to understand. First two equations in plane part of the problem, the third equation is out of plane part of the problem. Next, we know now in cases A and B, we said that the solution for case A and B is the same. I mean, we have found it. It is not that we are just saying it, we have calculated and it comes out to be the same. And what are cases A and B? In both the cases A and B, the lamination sequence is symmetric, which means that B matrix for case A and B matrix for case B is 0. Okay. Now, in plane part of the problem involves nx and nxy and nxy and ny. In plane part of the problem means these first two differential equations which involve only nx, nxy and ny. Out of the plane problem involves mx, mxy and my and q. Okay. Now, let us look at nxy, nx. From our ABD equations, what is nx? Nx is equal to a11 epsilon x naught plus a12 epsilon y naught plus a16 gamma xy naught plus b11 kx naught plus b12 ky naught plus b16 kxy naught. And because the matrix is symmetric, these terms go away, the b terms go away. So, nx, so what that means is that nx only depends on epsilon x naught, epsilon y naught and gamma xy naught, because B matrix is 0. Similarly, nx, ny and nxy, we can say the same thing about all the n's. Okay. Now, we know that epsilon x naught is del u over del x, epsilon y naught is del v naught over del y, and gamma xy naught is del u naught over del y plus del v naught over del x. So, we can say that nx, ny and nxy, they only depend on u and v, midplane u and midplane v. Okay. This is because, so which means that if we look at the in plane problem relates to the first two equations, these involve only nx, nxy and nxy. The solutions for nx, ny, nxy, they only depend on the nature of u and nature of v, okay, when B matrix is 0. Okay. So, I can make a further statement that solution of in plane problem only involves u naught and v naught. It does not involve w naught. If B was not 0, then it would have also involved w naught, but in this case B is 0. So, it involves only u naught and v naught. Similarly, we look at the third equation. The third equation involves only mx, mxy, my and q. Okay. And so, we will see, for instance, mx is equal to what? b11 epsilon x naught plus b12 epsilon y naught plus b16 gamma xy naught plus d11 kx naught plus d12 ky naught plus d16 Kxy naught. Now again, because the lamination is symmetric, these things go away, and Kx we know they only depend on W. They only depend on W. So we know that Mx, and for similar logic My and Mxy, they only depend on W so in case A and B, they only depend on W. And if you look at the third equation, which is out of plane equation, it only involves Mx, My, Mxy and Q. So we can also write that the solution to out of plane problem only involves W naught. Okay. So this is one statement, solution to out of plane problem involves only W naught, and the other statement we made is solution to in plane problem only involves U naught and V naught. So the solution for U naught and V naught does not influence W, and the solution for W does not influence U and V. This is what it means. So in this case, because the lamination sequence is symmetric, the out of plane and in plane parts of problem are decoupled. Out of plane part of the problem and in plane part of the problem are decoupled. The solution for W does not influence the solution for U and V, solution for U and V does not influence the solution for W. This is happening because the lamination sequences, because this B matrix is 0. Okay. B matrix is 0. So that is one case. So solution of U and V does not influence W and vice versa. Now our original question is, why is the solution same for case A and case B? So to see that, let us look at this picture again. What this means is that so the solution for case A and solution for case B will have an in plane solution. The in plane solution will involve U and V, and it will have an out of plane solution, and that will involve W, and the in plane solution and out of plane solution are decoupled, because in both the cases the lamination sequence is symmetric. Now let us look at these boundary conditions and see what are the in plane boundary conditions. So U is in plane boundary condition, V is in plane boundary condition, Nx is in plane boundary condition, and Nxy is in plane boundary condition. What are out of plane boundary conditions? These two are out of plane boundary conditions. So in case B and case A, out of plane boundary condition, I have put it in red box. Okay. Now when you look at the out of the plane problem for case A and case B, you see that out of the plane boundary conditions are identical. W is 0 at both ends, and Mx is also 0 at both the ends. So out of plane boundary condition is identical. Also the lamination sequence is identical, the length is identical. So if the geometry, so the out of plane problem, the boundary conditions are same, and also the lamination sequence is same, length of the plate is same, and because so the solution will also be the same, because this solution will not get influenced by in-plane boundary conditions. It will not get influenced by in-plane boundary conditions because the situation is decoupled. Okay. So, for that reason you see that the expression for W is same expression for. So, this is the out of plane boundary out of plane solution, and it is same out of plane solution. Why is it same? Because the out of plane boundary conditions are same, geometry is same, and lamination sequence is same. Okay. So, the solution will also be same. Okay. The solution will also be the same. That is the thing. The other thing is that we also see that in plane solution is also same. So, this is the in plane solution. Now, in plane solution is same because effectively in the in plane I am not putting any external forces. If I am not putting any external forces, then everything will be 0. So, for this reason the out of we see that for case A and B, out of plane as well as in plane solutions are same, even though the boundary conditions are different. This will not happen when we start dealing with non-symmetric lamination sequences, and we will actually see this. So, this is what I wanted to discuss in today's lecture, and we will meet once again tomorrow and continue this discussion further. Thank you.